Okay, welcome to lecture 12.3. Um, this, I think, is going to be go quick. I'm just going to explain Levitt's paper written in the AER. Gosh, I can't remember when. I think it was like 1996, um, called How Senators Vote. And all Levitt did is he said, uh, look, there's various factors that go into the senator's vote. One, his or her own ideology, his or her constituency, his or her primary constituency. So your constituency, you have the general election, you got to win that, but you also have to win the primary election. So if you're a Republican senator, it might be important what the Republican voters in your district think, as well as maybe what the median of the entire district thinks, or the state. Um, and I think I mentioned, and then also maybe the party. So you could be pressured by other members of the Senate. Say if you're a Republican, your fellow Republicans may pressure you, or the Republican leader. So Levitt's going to posit that your vote is just a weighted average of all of those influences, and then he's going to estimate what are those weights. Okay, so uh, and the way he does it, he has a structural model. Okay, and we're going to go through some of that structure, and I want you to learn some of the things. There's some kind of convenient assumptions he makes, and those make the estimation procedure pretty easy. Actually, it turns out that it makes the estimation procedure, you can do it by regression. Okay, so here's how it works. Okay, um, first, some terms. Okay, VIT just equals um, Senator I's adjusted ADA score in year T. So the adjusted ADA, that's from our paper, my paper with Levitt and Jim Snyder. By the way, so the paper, the adjusted ADA scores, um, was inspired by this paper. I was talking to Levitt one day, and he was telling me what he's going to do using ADA scores. And I said, well, wait, but they change over time. The scale changes over time. He said, no, they can't. That's not. It's minor if they do that. And we thought, oh, okay, let's talk about what a model would look like. How would we estimate if those scales change? We said we ended up doing a paper on it. But it was all because of this his first paper, this House Senators Vote paper. Um, okay, VIT. Right, next, SIT equals, he called it bliss point. I usually call it ideal point. Bliss point of, let's see, he calls it the voters in state I. I'm going to call it the median voter. Bliss point of median voter in state I. And by the way, this is on the ADA scale. So he's saying this the bliss point, the median voter of the entire constituency, not just the primary election constituency. And that is on the ADA scale. So he can't observe that, or maybe there's a way to observe it, but he doesn't. So instead, what he does is he said, well, the ideal points of the House members in I state is a good proxy for the um, ideal point of the median voter in state I. Okay, next SIT. Okay, CIT equals bliss point of median of I's, calls it CIT, support constituency. Support. And this means the ideal point of the primary constituency. And in practice, what it's going to be, if Senator I is Republican, so CIT is the ideal point of the Republican House members. It's going to be a proxy for the Republican voters in I state, but he doesn't have the date on the voters. Okay. PIT equals bliss point of I's party. Let's see, i.e., fellow senators of same party. Okay. And the way he's going to operationalize this, he's going to do it one way where he estimates the average ADA score of the party of the leaders of I's party. I think it uses the, let's say, if they're the majority party, the majority party leader, the majority whip. Maybe there's a third one. I can't remember. The one is to do it that way. Then the other is to just use the average of all the party members. So he takes the average, if I's a Republican, take the average of all the Republicans in the Senate, and then that's going to be PIT. Okay. And then he has a Z sub I. Okay, notice that it doesn't have a sub T. Okay, this is I's own ideological bliss point. Okay, so this is what Senator I's the ideology he feels in his own heart. Okay, so and what he's going to assume is this VIT is a weighted average of these four factors. Okay, so that's where we're going. Notice that ZI does not vary over time. It's basically going to be it's sort of kind of a fixed effect for Senator I. So we're going to estimate it. We can't allow it to have a different one each year. We'll have an identification problem. So he does the simplest thing, just assume that it's constant throughout the entire career of Senator I. Okay, those are some definitions. Okay, VIT, that's going to end up being the dependent variable when we do this regression. SIT, CIT, and PIT are going to be independent variables. ZI is going to be a coefficient that we estimate. Okay, so keep that in mind. It looks like ZI, often we've used it as indicating an independent variable. It's going to be a coefficient. Okay, everything else is data. Okay, so now, all right, so here's the structure. Okay, Levitt assumes that Senator I's utility function equals a weighted average of these other utility functions, or these aspects of utility. In particular, what I mean here is that UIT equals alpha times his utility from voting with his support constituency, the SIT, bliss point. No, the state, of the voters in the state. So this is negative VIT minus SIT squared. Okay. So for now we're in the theory world. Okay. So the SIT, call that's an independent variable. Let's say we can observe that. VIT is going to be how the senator votes. That's going to be his ADA score. So he's going to choose what his ADA score is. So how often he votes on the liberal side. So that's going to be a parameter that he maximizes. So pretty soon we're going to take I'm going to write out this utility function. Then we're going to take the derivative of it with respect to that VIT, the one thing the senator gets to choose. Okay. So it's a weighted average of the alpha times his utility from voting near his voters, SIT, the support constituency, Bliss point. Okay, plus beta times similar term, negative VIT minus, notice this is a quadratic utility function, okay? Remember that. When you assume quadratic utility, it makes things simpler, especially if you're going to have to take a derivative, okay? So we'll get to that in a second. So negative VIT minus CIT squared, and this is the support constituency. So the senator's Republican. This is like the bliss point of the Republican voters in his state. SIT is the bliss point of all the median of all the voters in his state. Okay, so his utility is a weighted average of those two sort of sub-utility functions plus gamma times negative VIT minus PIT. Okay, PIT, that's the bliss point of his party, his fellow Republican senators, Republicans in the Senate. Okay, and plus just the remainder. So he's going to constrain the weights to sum to 1. So the last weight is just the 1 minus alpha minus beta minus gamma times negative VIT minus ZI. Okay, ZI, remember, is what he feels in his heart. That's his ideal point, his own ideology. Okay, we do that. All right. We're now just going to take, so this is Senator I's utility function. Okay. Let's take the derivative of the utility function with respect to VIT. I said that's going to be a variable that he can choose. So we have delta UIT D VIT. What we get is alpha times negative 2 times VIT minus SIT. Okay. Plus beta times negative 2 VIT minus CIT plus gamma times negative 2 times VIT minus PIT plus 1 minus alpha minus beta minus gamma times negative 2 VIT minus ZI. We're going to set that equal to 0. Okay. All right. What happens? First of all, we can cancel out the negative 2's. Okay. So multiply both sides by negative 1/2. All the negative 2's cancel. Okay. So what we're going to get, and then we collect all the VI terms. We're going to have an alpha times VI plus beta times VI plus gamma times VI plus 1 minus alpha minus beta minus gamma times VI. Okay. All of those, use the distributive property. all of those terms add to 1. Alpha plus beta plus gamma plus this, 1 minus alpha minus beta minus gamma equals 1. So when we collect terms on the VIT, the constants will equal 1. So we're going to get VIT equals, well, actually it's going to be minus alpha times SIT minus beta times CIT, but let's put them on the other side of the equal sign. So let's add alpha SIT to both sides. So we get VIT equals, okay, alpha times SIT plus beta times CIT plus gamma times PIT plus 1 minus alpha minus beta minus gamma ZI. Okay, so Levitt says, okay, that's my theory. VIT should equal that. He says, well, the theory assumes no uncertainty. Let's add an error term, okay? Plus epsilon IT. Okay. Great thing is most of these are independent variables. SIT, CIT, PIT. ZI is not. We'll talk about them in a second. But if we could observe it, this would just be a simple regression. That's how we would estimate this. Okay, I mean, we could, put in the PDF of the epsilon IT, and we could show how the likelihood function that this implies is the same thing as a regression. So maximizing it would just give the same coefficients as we'd get from doing a regression. Okay, now there's some structure to it though. So it says it's a regression, but notice a regression that there is no intercept term. Okay, our theory says we should not have an intercept term. Okay. Next, we're going to have this term. So we're going to have to, this is going to be a little tricky here to estimate that. Okay, because we have a series of coefficients times another coefficient. Okay, so now let's talk about how we're going to estimate that. Okay. Here is what Levitt does. Okay. All right. So he's going to say that, how is it? He's going to estimate this. VIT equals alpha times SIT plus beta times CIT plus gamma times PIT, okay, plus, what does he do? He's going to say plus delta I plus epsilon IT, okay, where we're going to assume that delta I equals 1 minus alpha minus beta minus gamma times ZI, okay? So we've just defined that to be that term. So here's what we had before, okay? VIT equals alpha, this blah, blah, blah. So we're just going to redefine this term as delta I. So we're going to estimate delta I, okay? Now here's what's going on. If we could estimate delta I, now if somehow we could do this regression or use this estimation technique and get an estimate of alpha, beta, gamma, delta I, where that delta I is different for each senator, but say we look at just one senator, so we know his delta I. Suppose we've also estimated alpha, beta, and gamma. Then all we got to do is plug in delta I, whatever our estimate is of it, plug in our 1 minus alpha minus beta minus gamma, our estimate of that, divide delta I by that, and that's going to be an estimate of Zi. So I said Zi is going to be a parameter that we estimate. That's how we're going to do it. Okay. All right. More specific, here's what we're going to do. We're going to create what we often call a fixed effect for the senator. So in particular, we're going to have this term, big I sub IT equals 1 if observation T. So I made that T years, but now let's make it, sorry, I'm switching notation. T is which observation. So we have this data, and we have rows of data. So T is now the rows rather than the year. Okay, sorry, I'm changing this a little. Okay, but so we're going to find IIT equals 1 if observation T involves senator I and 0 if not. Okay. So here is what the data is going to look like. So suppose we have the year, we have the senator. We've given a different label for each senator. There's Senator 1, Senator 2. So somehow we've put a label on these. Suppose we've got year 1981, 1982, 1983, 1983. And suppose this is the way we've ordered our data. The first 3 rows involve Senator 1. The second 3 rows involve Senator 2. And let's say Senator 2 served in 1967, 1968, 1969. Okay, now the next thing we could put the VIT. So this is the adjusted ADA score of Senator I. We could put SIT. So what Levitt does is he says, well, in 1981, let's look at the average House ADA score of all the members in Senator I's state. That's SIT. Okay, so all those variables, VIT, SIT, so on, those are easy to code. Okay, here's what's going to be hard. Okay, so we're going to have first, okay, let me go to subscript. Okay, so I1, comma T, I2, comma T, and I3, comma T, and so on. So I think there's something like 300 senators in this data set. So we're going to have this indicator variable, we're going to have 300 of them. So in each one is going to be a vector of zeros and ones, and it's going to look like this. So don't worry about VIT, but I1IT, so that's going to be a 1 for observation 1, also a 1 for observation 2, 1 for observation 3, but that's going to be zeros for all the other observations. Okay, we're assuming, say, Senator 1 only served in these 3 years. So it's going to be zeros all the way down. Senator 2, the IIT, is going to be a 0 for the first 3 observations. And then, let's see, 1970. And then it's going to be, so let's assume that Senator 2 served in only 4 years, these 4 years. So then he's going to have 1, 1, 1, 1, and then zeros. Okay. Person 3 is going to have something similar. So what we're going to have is these vectors of 1s and zeros. All right. Okay. Then what we're going to do is we're just going to have the regression. We're just going to have VIT equals alpha times SIT plus beta times CIT plus gamma times PIT plus delta 1 times I1 comma T plus delta 2 times um, I2 comma T plus delta 3 times I3 comma T and so on. So we're going to have like 300 of these terms, the delta I times the indicator variable, okay? So now this is just a regression. So this is a regression with, here's our dependent variable, and we've got maybe our three main independent variables, and then a series of indicator variables. These are all vectors of ones and zeros, and there's 300 of them. And then we're going to estimate 300 coefficients, these deltas. So all this is a regression. So you just type in to Stata or whatever, regress VIT on these three independent variables plus these 300 indicator variables. Actually, it's even easier than that. I think there's a way to, if you have some experience with fixed effects, you can say something like put a fixed effect for these senators. I'm not comfortable with that. I haven't done that. Instead, I like to think of it as vectors. So I would instead, if it were me, I would create a spreadsheet with 300 of these vectors of these I sub IT variables. But once you do that, oh, and then you also got to tell it, you got to tell Stata or whatever, SAS, don't estimate a constant, okay? Just about all stat packages have such a command. Once you do that, then you've got it. You've got an estimate of alpha, beta, of gamma. And then I said ZI is just going to equal, what did I say? What did we say? So we said that delta I ZI equals, how do we do it? Delta Zi equals 1 minus alpha minus beta minus gamma times, gosh, why am I forgetting all this? Oh, here we go. Delta I equals 1 minus that times Zi. Okay. Yeah, that's delta I. Delta I equals that. Zi, so that means Zi, our estimate of it, Zi hat, is just going to equal delta I hat divided by 1 minus alpha hat minus beta hat minus gamma hat. Okay, and that's it, okay? That is how we're going to estimate all these. Okay, one little tricky thing. Usually the Stata will report the standard errors of the alpha, beta, and gamma. That's going to be easy. The standard errors of the Z's, the ZI's are going to be a little tricky. You could have the standard errors of the delta I's, but this is going to be actually kind of a mess. But I'm not even sure Levitt reported standard errors of the ZI hats. Okay. So that's it. So key is, so he has the structural model. You could use it to create a likelihood function, but we showed that the likelihood function is going to be identical to a regression. So Levitt did a regression with one added little trick. You have to put in these vectors of these indicator variables for Senator I, and then do this second trick. You get Zi is just going to be the delta divided by the other coefficients. What happens? Okay. Give. Wait, I've run out of. No, I've run out of board space. Let me say what the results were. He got alpha I hat. This is the weight on your support constituency, on the voters in the general election from your state. That was about 0.13. Beta hat, not I, just alpha hat. Beta hat was also about 0.13. Um, Gamma hat was about 0.14. And then 1 minus alpha hat minus beta hat minus gamma hat equaled about 0.6. Okay, so what that says is you put the weight of how you vote. 60% of the weight is on your own ideology. 1 minus that is the remainder. That's your own heart. Okay, and then you put about equal weights on your party, the voters in your general election, and the voters in your primary election. Interesting, Levitt did this again. He said, what if we estimate it just for the senators who are near re-election, say they're in the last 2 years of their 6-year term? And what did he get? Yeah, sure enough, the alpha and beta, the coefficients go up in those cases. Let's see. Final thing, he estimates the ZI. He reports those for different senators, and it's interesting. So it says, it says it's an estimate of what people's ideology is in their heart. So you take out all those other factors, and he got things like Jesse Helms, noted conservative. He was a -13, as you might guess. Levitt estimates Jesse Helms really was very, very conservative in his heart. He got, let's see. He reports them in the paper. I encourage you to look at that. The one kind of curious, you got Al Gore was 59. You got Al Gore, and his heart was a moderate. I'm a little skeptical of that. I think we learned after Al Gore left the Senate, he seemed pretty liberal to me. So that may have been one questionable result I have from the Levitt paper. So you have that. Okay. A final point. Okay, so this is it. I'm going to end on this paper. And this is my last lecture, except for my meetings with you all in person. One thing I want to talk about is Levitt's results, something kind of interesting. And I want to go back to something that I said in the last part, something witty that my old colleague from UCLA, Jeff Lewis, said. He said, Stata will do what you want to do, but you got to trick it sometimes. Jeff Lewis has another really clever thing. So after seeing these results from Levitt's paper, Jeff Lewis said, if I had done this paper, no way would this have worked out that cleanly. It never works out for me like this. No, he said, Jeff said, if I had done this paper, I would have gotten some negative estimates on some of these weights. And I would have gotten some weight had a weight, one of these coefficients would give a weight of greater than 1. When I do something like this, it never works out for me. So for some reason, it always works out for Levitt. Okay. Now, maybe Jeff was thinking of this, that, Levitt's fudging his results to make it so they just work out. So the referees of the journals are going to say, oh, yeah, that makes sense. Oh, let's accept it. I have a different theory about what's going on. And this is that Levitt, I saw him in person. We were together at MIT in the mid-90s, and I met him when he was a grad student, and I watched him up close. This guy has so many ideas. He is producing like 2 ideas like this a week, okay? He has so many of these ideas that there's no way he can write the paper for each of these ideas. So what I've observed is he will quickly do some sort of pilot project, just get a little bit of data, see if it seems to make sense. If it does, he'll write the paper. If he doesn't, he abandons it. So the reason all the things seem to work out for him is we don't see the papers that he abandons. There's lots of cases where it doesn't work out, and we don't see that. So that anecdote, okay, I want to end on that. So a lot of you are now in the stage. So no more homework, but the key is now you've got to come up with your idea for your presentation, a project, and do a presentation for a potential project that you'll do. Hopefully a dissertation chapter, hopefully a published paper, and you're going to present that to me and your fellow classmates. You're going to meet with me to talk about your idea. Let's learn from Levitt, okay? To have a good idea of a published paper, the key is to have lots and lots of ideas and then weed out the bad ones, okay? So I think I've told you earlier when we met in person, I said, look, you've got an idea. We're still kind of early in the semester. We've got a few weeks. At least right now, don't get wedded to one idea. Try to think of lots and lots. I'd encourage you at least 3, maybe more. And if they're just half baked, you need only a minute or 2 to talk about it. Maybe we can weed it out very quickly. But try to come up with lots and lots of ideas. In fact, even a great scholar, Karl Popper, the philosopher I've talked about before, he has said in one of his writings that maybe it's the case that it's not true that some people have better ideas than others. Maybe what's really going on is that some people just have more ideas than others. And the ones that we see with good ideas are the ones who just have lots and lots of ideas, and they've weeded out and discarded all the bad ideas. Okay, so let's try to learn from that. Try to do Popper's prescription. Think of lots and lots of ideas, and then we'll talk to me, and we'll try to weed out some of those that aren't so good. So the key is, and even if, like I said, if it's just a half-baked idea, write it down, and let's talk about it. It may turn out to be a great idea. Okay, so that's it. That is my last lecture. It's all up to you now. Start thinking of ideas. Okay, and I will see you guys individually in person very soon. Okay, see ya.